Ever wonder what the secret language of explosive growth is? Well, today we're going to dive right into it. We're talking about exponents. And we're going to meet their secret identity, the tool that lets us work backwards, the square root. So, to get started, let's think about something that grows, well, insanely fast. Imagine a single bacterium. Every hour it splits into two. How on earth do you keep track of that kind of growth? You start with 1, then it's 2, then 4, 8, 16, and pretty soon you're writing out this super long, messy string of multiplications. After just a handful of hours, the numbers get huge, and honestly, it's just a pain to write down. But what if I told you there's a much cleaner, way more elegant way to do this? Instead of writing 2 times 2 times 2 times 2 times 2, we can just write this, 2 to the power of 5. And that is the power of exponents. It's this brilliant little shorthand for repeated multiplication. And look, this isn't just some neat math shortcut. It's literally the language we use to describe how things in the real world grow, from our little bacteria friend to how money multiplies in a savings account. It's the language of compounding change. So let's really build our understanding of this from the ground up. What exactly are these powers? And, how do they actually work? Okay, so an exponent is basically just an instruction, a command. It tells its base number, in this case the number 3, exactly how many times to multiply itself. So 3 to the power of 4 isn't 3 times 4. No. It's 3 times 3 times 3 times 3, which lands us at 81. Now, to get fluent in this language, we gotta know the vocabulary. First up, we have the base. That's the big number being multiplied, like the 5 you see here. The exponent is that little number up top telling us how many times to use the base. The whole thing, 5 squared, is what we call exponential form. And the final answer, 25, that's standard form. Pretty straightforward, right? Okay, so we've seen how to build a big number from a small one. But what if we need to go the other way? What if we have the big final number, but we need to figure out what number we started with? Just picture this. You've got a perfect square garden, and the total area is 81 square meters. Now, area is length times width, but since it's a square, the length and width are the same. So the real question is, what number times itself gives you 81? And that is the job of the square root. It's like our own mathematical detective, designed specifically to find that original root number that got squared in the first place. And this shows the relationship perfectly. They're inverse operations. Squaring a side of 9 gives us an area of 81. And taking the square root of that area, 81, brings us right back home to the side length of 9. They perfectly undo each other. But hold on, there are rules. You can't just go wild with these things. Let's do a quick pop quiz. What do you think? Can you just split up a square root like this? Is the square root of 9 plus 16 the same as the square root of 9 plus the square root of 16? And the answer is a big fat no. You can do that. As you can see, if we do it the wrong way, we get 3 plus 4, which is 7. But the right way is to solve what's inside the root first. 9 plus 16 is 25, and the square root of 25 is 5. See? Totally different answers? Okay, so we've got exponents for building things up and square roots for finding where they started. They seem like total opposites, right? Well, maybe not. Let's pull back the curtain on the secret connection they share. So we have exponents, our engine of growth, taking a number and making it bigger, faster. And we have square roots, our detective, taking a big number and finding its origin story. Builder and detective, two completely different jobs, or are they? What if I told you a square root isn't a different operation at all? What if it's just an exponent wearing a clever disguise? And there it is. This is the whole secret. Taking the square root of any number is the exact same thing as raising that number to the power of 1/2. This is so cool. It means a square root isn't some new, separate thing. It's just a special type of exponent, a fractional one. Now that we've unlocked that secret, let's grab a few powerful rules for our toolkit and see how this stuff actually shows up in the real world. First up, we've got a kind of weird one. The zero exponent rule. Any number, I don't care how big, raised to the power of 0 is always 1. 9 to the power of 0, it's 1. 1,000,000 to the power of 0? Yep, still 1. Now, this isn't just a math party trick. In formulas for things like population growth or compound interest, this rule represents time 0. It's the single starting point, the baseline, before any of the growth has actually happened. It's absolutely essential. Next in our toolkit is the negative exponent. Now, you might think this makes the number negative, but it doesn't. Instead, it flips it. It turns it into a fraction. So 2 to the power of -3 becomes 1 over 2 to the power of +3, which gets us to 1/8. It's how we can write incredibly small numbers. And you see this idea everywhere. Scientists use negative exponents to talk about the size of an atom. Engineers use them for unbelievably precise measurements. And on the flip side, all that massive storage in your computer, measured in gigabytes, that's all thanks to the power of really big positive exponents. So in the end, that's really what this is all about. They aren't two separate ideas. They're part of one single elegant system. It's about power, the power to grow and balance, the ability to find our way right back to where we started. Once you master this, you unlock a key to understanding so much more about the world, which leaves us with one final thought. What other concepts in math that seem like total opposites are actually just two sides of the same coin? Something to think about. Thanks for watching.